I will be wandering around the stage because I like to point at my charts. So I hope to be able to add to the excellent presentations done by Daisy and Dennis, which this is very complimentary to. What I'll be talking about is operations of these timing networks. So start with basic introduction, which we've already had to some extent, is mobile applications will fall over without timing. Some other related applications, smart industry, finance, and so on, have similar requirements, but fundamentally, they fall over without timing. This is why we're going to talk about operations, how we keep them up. So, Dennis made an excellent case with his Baltic jammer of state-based actors. I would also like to add to that, we have seen some Russian warships going around the north coast of the UK and Ireland, which coincidentally happen to be aligned with a lot of GPS dropouts at the same time. Couple that with something Dennis referenced is this picture is taken from an eBay listing. If you were willing to splash out a whole 10 euros, you would be able to plug this into your delivery van, and you would not be able to be tracked by your boss as a delivery driver to see whether you're taking too long a breaks. I believe that was what Dennis was referring to. 10 euros, that's all it costs. GPS is incredibly easy to disrupt because it's such a weak signal. So this is very important, just how fragile the signal is. So you need resilience. You need a backup plan. And network timing is that backup plan, or even for some people, the primary solution. Dennis also referenced a national timing signal that is likely to be delivered purely via the network. So again, a need for network timing. If you are using network timing, you need to assure your network timing. It needs to work. So let me be much less delicate than the very cultured previous two presenters. No timing, no service. There's no point in having connectivity to your mobile's base stations if they don't have timing, because they cannot operate. So you must care about keeping your timing up just as much as you care about keeping your connectivity up. So there has been, the next step is an increase in a need for accuracy. Both of the previous speakers referenced this figure, 1.5 microseconds. I've chosen to put as 1500 nanoseconds of absolute time error required. However, many coordination applications, as Daisy referenced, need you to do better in terms of relative time error. This number is compatible with Daisy's, it's just a different way of looking at the budgets. We are also working with some people who are wanting to go further than that, up to the next step. This would be how you do multi-site MIMO, where you'd get down to 10 nanoseconds of relative time error. That's not a typo, that's 10 nanoseconds. I think probably most people in this room know the speed of light in fiber means that that is 1 nanosecond. So if you mispatch your fiber by a few meters, you have broken your timing budget. A few meters, not kilometers. This is how sensitive things can now get with the most advanced coordination applications. So getting timing across the network is a lot harder than it used to be. The world has moved on. So now I've scared you. Let's talk about how we solve the problem. We would recommend that you use a new protocol that we have submitted to the ITU called Assisted Full Timing Support. Many of you may be familiar with APTS. 3 things you should know. We have submitted it in standards. It is public. It is like APTS, but based on G8275.1 rather than .2. The previous 2 speakers have referenced this, but I'll go through it again. G8275.1 is a protocol where every hop you go through, you retime. I think everyone here knows that queues are evil when it comes to jitter. Queues introduce jitter into frames, timing hates jitter. G8275.1 will eliminate the PDV jitter from each hop. However, as previously referenced, where you cannot do that, where you have legacy or timing unaware devices, you must pass through using G8275.2, so we can mix and match using that legacy hardware. APTS combines the resiliency mechanism of the well-known APTS with that G8275.1 accuracy. And for those who are just waiting for the moment when I go through this in detail, you are very lucky. So, APTS is where you have a primary timing clock from a local GPS receiver. You have a backup timing clock coming from the network. However, that backup timing clock is a G8275.2 clock because your network is legacy nodes or incapable or otherwise problematic. So you have to go through transparently without retiming. In a non-fault scenario, this cell site router is sitting there using its local GPS as normal to run the network. However, it is also taking in the network timing and it is comparing the two. It is establishing a calibration factor. Therefore, when you switch over from one to the other, you should not get a glitch. So that's a huge improvement over basic failover. However, G8275.2 does not retime. It cannot control packet delay variation, so it will gradually drift off. It's good to start with, but can't hold on for that long. So contrast this with APTS, exactly the same thing, but using G8275.1 as backup. You have retimed this many times. My very nice marketing lady redid this chart for me, pointing out that with 8275.1 you can get 20 timing capable hops. She insisted on writing every single one out here, as you can see, as opposed to the 2 or 3 of .2. You have hugely more flexibility in how you build your network if you can build it using .1. Most importantly, because you are now locked to frequency and phase, you can keep that timing backup indefinitely. A huge difference. Let's talk about that in terms of the consequences on your actual network build rather than just the nerdiness of it. With APTS, you get high quality failover. The failover is good, but then you drift. If you have used coordination functions such as multi-site carrier aggregation, when you drift, you may step outside the tolerance they can handle, which may mean you can't use them, which may mean you do not get the efficient spectrum utilization you otherwise would from those coordination applications. A less efficient radio network, a less efficient use of that huge asset which most carriers have spent many billions of dollars or euros or pounds buying. Contrast that with APTS, where the PDV factor is eliminated. You can track indefinitely to that backup clock, which means you can use inter-cell coordination down to the level of accuracy you would normally have from that timing, which means you get more capacity from that spectrum you spent the billions of dollars on. You simply get more from your assets this way. Now, an obvious question here might be, well, it's really G8275.1 which is giving you the advantage here. It's not particularly the failover mechanism. So why don't you just fail over to G8275.1 and not use APTS? So let's look at that question. On the top, I have simple protection from GNSS or GPS to G8275.1. So in the non-fault case, again, I'm locked to the GNSS. I fail over to G8275.1, and I am locked indefinitely to my PRTC or ePRTC. Great. Sounds the same as the good one before, doesn't it? Contrast that with APTS, and now we spot the critical difference. Again, with APTS, in the non-fault scenario, I am sitting there calibrating that network backup. I am looking at the difference. And what that means is, in practical terms, the simple failover has a phase shift when you do the failover. Because even though the GNSS and the G8275.1 are perfectly aligned, in frequency there is a slight phase offset between them. So, phase shift is an error. Error means you may exceed your margin for being able to do coordination. Exceeding your coordination margin, again, you are not getting the most out of your radio spectrum. That may be a few billions less that you could have put into some executive's bonus. With APTS, you have no phase shift on failover or recovery, so you can use your inter-cell coordination, and you do have that more efficient radio network, so executives are laughing all the way to the bank, perhaps. So the difference is very clear, and this is why we would recommend it. If you have a network that is timing capable, there is no reason you cannot do this, because it's only the terminal node that needs to support APTS. Everything else is just simple G8275.1. So that has introduced our recommended technology. So now let's talk about operating it. Because I mentioned at the start, the whole thing is you are then dependent on the network. You must keep the network timing up. This is a software display showing tracing a clock source. So let's say this is my cell site router here. I'm tracing that I get my clocks, thank you, getting my clock source from there, from there, from there, from there, from there, and finally back to my microsemi grandmaster here. That may seem quite simple, but for those of you who have configured timing, you will know that if you did this with CLI, it would take you about an hour, because this clock will have multiple resilient inputs from there, from there. This one will have multiple resilient inputs from there, and that one, and that one, and that one, and that one. So you have many, many possible paths that could be feeding the clock to this cell site router. And quite honestly, I think it would drive you nuts trying to do that by hand as soon as it gets to a non-trivial number of hops. We think it is simply not practical to do this without software tools. I would add to this what else is being displayed here. You can see this tiny icon of a padlock indicating that all of these nodes are locked to their grandmaster. Great, that's how it should be. But the first thing you want if you are having timing problems is, are any of them not locked to their grandmaster? We'll look at a more complex case in a second. So this simple display in one thing is telling you exactly what you need to know to find out any timing problems to this cell site router. In many respects, it's hiding a lot of the work that my excellent colleagues have been doing to get it there. I'd also look here at the amount of data it's showing you, the clock class, the clock accuracy, how long these have been locked, what type of technology, G8275.1, G8275.2. You need software tools like this to operate your network if you are going to make sure that your timing stays up, because if you don't know it's down, you can't fix it. It's a highly resilient network. If you lose your primary path, you won't know. If you lose your secondary path, you won't know. Only if you lose your final resiliency path and it all goes down will you know, unless you have some kind of operational system attached to it. So I am certain that the one thing that is springing to your mind right now is that timing is all too simple, and what we need is to look at a more complex case. And you are in luck. So now let's look at a much more exciting case. In this case, we are using APTS, and we are going to look at the case where the GPS has failed. If you look closely at that top yellow icon to the top right, you will see there's a little GPS antenna icon that looks very different from this one, because that GPS input has failed. So I'm in an APTS situation where I have calibrated my backup and now I need to use it. Conveniently, I do have a backup down here. However, that backup, oh, missed a step, I beg your pardon. You can see I've failed over to that PTP backup from the antenna input. My backup grandmaster, as you can see, is down there. And however, that one is G8275.2 because we have a non-ideal hop here. Perhaps we've got a third-party leased line that we have to use, or maybe there's some kind of legacy node in the middle. So at that point, we can do profile interworking. We can translate from .2 to .1. So you can see I'm using a .1 link at the top. I would recommend that anyone who's in this situation does that, because every .2 link adds more error. every .1 link effectively doesn't. So if you get out of .2 as quickly as you can, you will reduce your end-to-end error. So you can see this map is now showing those multiple technologies. .2 here with this dashed line, .1 up the top with that solid line. And I hope everyone can see the key, which, needless to say, the graphical design people argued about for many, many hours. You can see also that there is a huge amount of additional detailed data being shown here for those who care about such things. So, in other words, we have established how important timing is. We have established that your network falls over and dies if your timing dies. So you need to verify and operationalize it just as much as you would with your connectivity. I have now shown you some sample tools that allow you to do that, and I hope it is clear that without these tools, trying to do this via CLI, when this is a function of a huge number of different nodes, would be practically impossible. So, software tools essential. I just want to summarize with a very beautiful picture of a satellite that PowerPoint kindly provided. Summarize the points of the message. Better timing gives you more performance from your 5G spectrum investment. So that will directly relate to cost savings before you have to buy new spectrum. There are serious financial implications of this. Therefore, coordination functions are generally being discussed as 5G goes forwards, and indeed 4G to some extent. However, if you use that better performance, you become dependent on highly resilient timing. Dependent. Your revenue requires that timing keeps operating and operating reliably. That means you should start looking at resilient timing technologies. We recommend APTS depending upon your needs. You may not need to do that, but if you are using G8275.1, there's no particular cost to this. Secondarily, once you are resilient on high precision time, you need operations tools to keep that network up. So, that concludes my presentation, and I would simply like to end by saying, please come and see us on the Sienna booth where we can talk about that particular timing application, how it works. And for anyone who didn't see it earlier today, unfortunately, in the wrong order here, there was a timing interop demo as part of the EANTC lab, and if you go and visit them, you can see that timing all working together between the many vendors. Thank you very much.